start. Is it recording? Yay. Okay, so welcome to, that's all right. Welcome to lecture 7. This will be about lighting, offshore wind, gadgets, and waves. But first, wait, call before midnight. It turns out that a famous author, Daniel Yergin, is going to come to Ohio State in April. And he wrote this book, New York Times bestseller. This guy won a Pulitzer Prize. This is about energy. This is called The Quest, Energy Security and the Remaking of the Modern World. Peter, was it you that was telling me you've been reading this and it's awesome?
Spencer.
That was Spencer. He's not here. Well, too bad. So I don't know what this guy's connection to Ohio State is, but he's going to come here. And so the College of Engineering bought a bunch of copies of his book that they want to give to people in classes about energy and sustainability, i.e. you guys. And they're hoping that we'll assign you guys to read at least some of this book. And then when he comes in April, they'll have a time when we can have a class and he'll come there and discuss it. So, believe it or not, each one of you gets this free book. Happy birthday. Sure. I've just started it, so I haven't decided what to ask you to read for your assignment. But so far what I've read is fascinating. So you probably just want to read the whole thing just because you can. And don't say your university never gave you nothing. For you distance guys, I'll stand over here. For you distance guys, what I'm planning to do is leave boxes of these books in the main office of the Electrical Engineering Department, which is 205 Dries Lab. Dries is on the corner of 19th and Neal. It's a very tall building, has a big cylinder on top, nobody knows why. And if you go to the main office and tell them your name, you can pick up a book and they'll cross your name off. So I don't know your name. What's your name? So I can write it down on my list that you got a book. Yeah.
Matt.
Matt, thank you. You're probably the only Matt in the book, so I'm just going to make sure that you don't come and try to get another one from me. All right, now I'm going to press preset. So you think the rain will hurt the rhubarb? Close up the podium and right screen at 7. Yes, that is what our distance folks are accustomed to. All right, so let's see. First of all, I found some more heating and cooling data. I've been trying to develop these stacks for Ohio, and we didn't have a good handle on the heating and cooling contribution. We said some fluffy things and we didn't have some good numbers. So after our last class, I was frustrated by that, so I went out and I found some more heating and cooling data. This is from the EIA, I forget what government agency that is. But this is estimated U.S. residential electricity consumption, and this is 2010, so the last data I had was 2001, and it wasn't broken down as nicely. So this actually says space cooling, lighting, water heating, as opposed to space heating, clothes dryers, cooking, dishwashers, freezers, clothes washers, and so forth. So this is great data, but use with care. This is only electricity. So most of us heat with gas, some of us cook with gas, so if you're doing heating and cooking and water heating kinds of calculations, you have to take into account that you're not considering the gas uses. Just thought I'd share that with you. So here's an opinion poll. Which kind of clothes dryer should you buy? An electric clothes dryer, a natural gas clothes dryer, or a clothesline? How many people want to buy an electric clothes dryer? Nobody. How many? Oh, you said maybe?
Me.
Maybe? How many would like to buy a natural gas clothes dryer? Yeah? How about a clothesline?
Depends where you are.
Exactly. I would love to have a clothesline, but my neighbors would not appreciate it.
Not only that, it's so humid here in this area and the East Coast that it's not going to dry out.
It does dry, but it takes a long time.
Oh.
And if it's raining like today, it's a very rainy day. I'm thinking that. And also in winter, clothes freeze. Yeah, so, but you're right. But of these two, I don't know which is more efficient. This is just a propaganda kind of question. So here's the stack that I've been developing for Ohio, or we've been developing collectively. For car and plane, I use the same estimates as for England. I suspect we fly more, but I haven't been able to prove it. So I just used his estimate. His estimate, remember, was based on one very long plane trip per year, like from London to South Africa. And like I say, I suspect the average American flies more than that, but I don't really know. And I also took his stats and I squished them down so that this is jet planes and heating and cooling, came to just over 100, so that we could see these things on the same scale. When I did an estimate for heating and cooling, I came up with 91 kilowatt hours per day. So that really jacked up our stack. You can see that his estimate for England was closer to, I think it's 37, maybe it's 47. I think it's 37, and this is 40 for car. For us, it's a lot more than the car estimate. Who knows if my estimate is right? So I had to juggle some numbers. If you want to see my math, come and see me during office hours. I'll go through it. But on the other hand, we had about the same wind. We have more solar. We have more solar farm potential because we have more areas per square person and slightly better light. This is PV personal. Biomass, Ohio is a nice agriculture area. And here's hydro. So this is the Shaughnessy Dam and by the zoo and a couple others. So that's where we look so far for Ohio, at least according to my estimates. Now let's talk about lighting. I love this picture. This is taken from space. Very good. Alert student Farzad. Yeah, this is taken from the space station, I believe. And you can tell where people live. All right, so I think there's a low density population here. I think there's a high density population here, high density population here, high density population here. It's amazing you can see all that light from space. So that tells you, doesn't it, that we're wasting a lot of our light. So you see more and more street lights and outdoor lights that are aimed so that the light goes down. The idea is you're not shooting it up into space. Of course, if you're just absorbing it in some kind of a black thing, that doesn't help. What you want to do is reflect all the light so that the stuff that would have gone up goes down and you get it. So lighting would consist of lighting in homes and in business buildings, and then also public lighting, traffic lights, street lights. What about architectural lights? Here in Columbus, we have the Levesque Tower, and they shine these beautiful lights up at the night, if you've ever seen that. And they change the colors depending on the holiday. Dries Lab is lit at night. Looks pretty cool. The stadium, you can see the stadium at night. There are some people who say we should get rid of architectural lighting because it's just for appearances. It takes a lot of energy. So let's see if we can get a handle on lighting. Here's a slide about office buildings in the U.S. So this says site energy use in office buildings in the U.S. This again comes from EIA, I forget what that stands for. And here, a quarter of it is space heating. More of it is lighting. Here we have water heating, other cooking. Well, in office buildings you don't do that much cooking, a little bit of Pop-Tarts, I guess. Cooling, I'm surprised it's as small as that compared to heating. Ventilation, so that's the fans just to keep the air running so we don't suffocate. Office equipment, these would be your computers and copiers. So lighting represents about a third of the electricity usage in office buildings. Existing energy efficient lighting technologies can reduce electricity usage for lighting by 20 to 50% in office buildings. And we're starting to see that. And actually, fluorescent lights are much more efficient than incandescent lights. This room has incandescent lights also. They're in those cans. Now that I've said that, I have to check. Halogen. Yep, I can see the filament. So that's incandescent. And we'll talk about some of these different kinds of lighting. If we could reduce, a reduction of up to 90% in lighting energy consumption are possible in residential situations. Basically, that's because most people are still using, well, I shouldn't say that. A few years ago, most people were still using incandescents because compact fluorescents were getting expensive, were pretty expensive. Now LEDs are starting to come into the picture. They're whopping expensive, but you don't have to replace them as often. So over the long haul, they may be cheaper. But lighting accounts for less than 10% of the energy use in the residential scenario. What are we using most of our energy for in homes?
Heating.
Heating and cooling, exactly. So when people say turn off the lights, yeah, do that, but turn down the thermostat. This is a cool building. This is 4 Times Square. It's a Department of Energy high-performance building showcase, a $500 million office tower in Manhattan. It has 10 to 15% lower operating costs than what? I guess a comparable building. I don't know what's lower than. $500,000 annual energy savings from what? It doesn't say. 5-year payback, I'm not clear what that means. But their lighting, let's look at how they're saving energy. High performance light fixtures, so they have fluorescent, HID is high intensity discharge lights, LED lighting, occupancy sensors, so when you go into the room, the lights come on. We have some classrooms like that. Low E glass, that's low emissivity glass. Curtain walls, I don't know what that is. Does anyone know what curtain walls means? I don't know what that means. Heating and cooling, they have natural gas absorption, chillers and heaters. I don't know what that means. Variable speed drives on pumps. So even my furnace at home is a variable speed fan, and that's supposed to be more efficient because it blows harder when it's doing more work, and when it's just keeping you alive by circulating air, it slows down. Occupancy sensors, sensor controls, and then they have generations. They have a 15 kilowatt photovoltaic installation, and I believe it's on the sides of the building, but I'm looking for it. I don't know where it is. I don't know if this is supposed to be it. And they also have 2 kilowatt fuel cells. So they have some generation power, which most buildings do not. Here on campus, have you ever been to the 4-H building over near the Schottenstein? 4-H building is a ultra energy efficient building. It's LEED certified. They have geothermal wells in the parking lot, and we're going to talk about geothermal energy later in the course, basically extracting heat energy from the ground, because underneath the ground, deep down, it's pretty much a constant temperature. So it's warmer than outside right now, and it's colder than outside in the summer. So they can get some heating and cooling. They have special windows that keep sunlight from getting in there and heating it up too much in the summer, so they don't have as much air conditioning. They have the room sensors that you go out into a room and the lights come on. If no one moves around, they go off. All the wall finishes and stuff like that are made out of bamboo and regenerable, sustainable materials. It's a pretty cool building. If you ever get a chance to go over there and wander around, it's kind of neat. So let's talk about lighting. There's lots of different kinds. And one of the things to pay attention to, so this presentation was largely prepared by a guy in Colorado who's a lighting expert, and so he has a lot of stuff in here. I thought it was kind of cool. So the color rendering index, you might see that on your light bulb package, and people don't know what that means, and here's what it is. It has to do with how close to natural sunlight is the color of those lights. So for example, fluorescent lights like we have here, are fair. So they might have well, let me say this, an incandescent bulb is 100, that's the highest. So that does a really good job of reproducing the spectrum of the sun, at least the visible part, and things look natural to us in incandescent lighting, okay? So that has 100. Fluorescents, 50 to 60 are standard warm white and standard cool white. 60 to 70, this is premium high pressure sodium, conventional metal halide. And when you look at people, they tend to have this kind of coolish cast. They don't look quite so healthy. And if you're shopping for clothes, you want to do it in a store that has incandescent lighting, so you get a better idea of the colors. Better would be 70 to 80 CRI. This is thin coat triphosphor fluorescent. And then down here in the really good range, 80 to 90, this is white high pressure sodium, warm metal halide, thick coat triphosphor fluorescent. And frankly, I don't know what kind of fluorescents we have up here. They don't seem as bad as these ones that I remember from when I was young. Incandescent and tungsten halogen. So this tungsten halogen is an incandescent light. There's tungsten gas inside the bulb, and there's a tungsten filament with a halogen gas inside the bulb, but it's still a filament, so it's still incandescent. This is the CIE chromaticity diagram. This is very cool. It's a representation of how to display colors to people. So, on the outside of this curve are monochromatic wavelengths. So if you had a laser, your laser is monochromatic. It would have a color, depending on its wavelength, somewhere around the perimeter. To get a color in the middle here, you have to use some combination of these wavelengths. If you are let's say you're a slide projector, and you want to project these colors, or if you are a computer monitor and you want to display these colors, which, whoa, look really different. Can you guys see this? I'm going to see if I can get the distance guys to see this. Probably they can't see both. That wasn't it. No, they can't see both. Oh, well, distance, guys. Take my... You can look at your own computer. Oh, wait, that's how they're looking at the slides. No, that's too bad. I already forgot what preset 7. 7 is the one I want. All right, so anyways, there's RGB, right? Red, green, and blue. Phosphors or light sources or something, pixels. And by wherever those things are, so let's say the red pixel emitted this color. Okay, it won't be pure because it's not a laser, but it emits this color, and then you have a blue one over here and a green one over here. That monitor can only produce colors inside that triangle. It can only produce colors that are combinations of the colors that you have as your sources. So white light is here, that's a combination of all of them. So here's an example of maybe 3 different kinds of monitors. These circles are the ThinkPad LCD. So that's a liquid crystal, and that can produce colors inside this part of the chromaticity diagram. The black dots are Sony, I can't read that, Trinitron CRT, cathode ray tube. No point in talking about that, nobody uses those anymore. This says PowerBook G3 LCD, that's the squares. I don't know where the other square is. Looks like it's here. Again, many colors, hard to display. The pluses are D65, whatever that is. So you have these red, green, and blue pixels. The quality of your display will depend on the size and shape of your triangle. So if you're building a high-end TV or movie theater, you're going to try to design your projector or whatever you have so that these points are as far into the corners of the CIE chromaticity diagram. And ironically, there's no way to accurately display the CIE chromaticity diagram. Even in print, there's no way. So it's impossible to reproduce color perfectly with RGB. Okay? Here's some lighting energy definitions. So when you buy a light bulb, if it's an incandescent, you might say, oh, it's a 60 watt or it's 100 watt. That tells you how much power does it consume. But what we really need to know is how much light do we get out of it. So the optics guys, we talk about luminous flux, and that's measured in lumens. So total time rate of flow of radiant energy, who cares? Here's what it means. 60 watt incandescent bulb will generate 850 lumens. 100 watt will generate 1700 lumens. So when you get to know these numbers, eventually you get a sense for what the lumens mean. Lumens, luminous flux, radiant energy, engineers are saying, oh, well, the flow of energy, shouldn't that be in watts or something like that, or joules or something like that? Yeah, but luminous energy takes into account the responsivity of our eyes. So things that are green they look brighter to us. We can see green better than we can see red. So things in the green range will have a higher luminous efficiency. So depending on the spectrum. Efficacy is different than efficiency. So efficacy is lumens per watt. Efficiency would be watts of light out versus watts of electricity in. That's efficiency. Efficacy is you put in so many watts, how many lumens, so how well does the light energy match your eyes? It's basically what that's measuring. So that's of more interest for lighting than plain old efficiency. Luminous flux emitted by a lamp divided by the total lamp power input, so you get lumens per watt. So this measures how well light source reproduces visible light. If you have a light bulb that converts all of the energy you put in with no losses to infrared, that is 100% efficient. It has no efficacy. So this, again, I'll just say this again. It takes into account, luminous takes into account the spectrum response of the human eye. Efficacy is in lumens. Efficiency would be in watts per watt. So the luminous efficacy of a candle is 0.3 lumens per watt. Now, how do you measure the watt input into a candle? I guess you have to figure out how much energy is in the wax molecules that you're burning. 60 watt incandescent bulb is 14 lumens per watt. Maximum possible theoretical, this would be 100% efficiency, and if it was all emitted at the thing that we see the best, which is 555 nanometers, which is green, then you could get 683 lumens per watt. That's the best you could hope to do. An ideal white light might be 242 lumens per watt. So putting some of the energy into other colors that we can see. This is a spectrum of the eye. This is 400, 500, 600, 700, just so you know. So this is ultraviolet. This is infrared. 555 is bing right there. Here is lumens per watt. Again, this is efficacy of different kinds of bulbs. My arm is getting tired. Here is incandescent, 10 to 17. Halogen, A line, is here. White LED, 20 to 60. Mercury vapor, I've never seen a bulb that looks like that. Has anyone ever seen a bulb that looks like that? No. I'm going to start a light bulb collection. I'll have to look for one of those. They seem to be pretty efficacious. Linear fluorescent. Ooh, they generate a lot of their energy in the visible spectrum. And depending on how good they are, you can see here there's quite a range. Compact fluorescent, smaller range. High pressure sodium. Up here, these I believe are used in streetlights. Metal halide. Up there. This is from dimmingballast.com.
Do you know how high pressure sodium lights work?
The question was, do I know how high pressure sodium lights work? No. I want to find out though. So that can be, actually I'll write that down. I will find out.
Yeah, I always thought that it was for the heating that it sometimes goes off, but now that you're saying that it's high pressure sodium, I'm thinking maybe is it because of the pressure that sometimes the lights of the street lights goes off and then after a while it just comes back on again.
Yeah.
So
I
it's
don't
the
know.
pressure or the heat.
I don't know. I have seen sodium light sources. I have them in my lab. They're not high pressure sodium, and I think there's sodium gas in there, but you know what, I don't really know, so let me find out and get back to you. It would be interesting actually to know how all of these work. So when you buy a light bulb, the specifications will be on there. The mean lumen output, so this is 2,700 lumens, and this one consumes 42 watts. So this is 42 watts electrical in, that many lumens come out. The lamp life, they're saying, is 12,000 hours. I haven't ever had a compact fluorescent last that long. No, I don't believe those numbers. This one costs about 10 bucks. What's the labor cost in manufacturing this? That's not on here. If you need an external circuit, for example, some of these need a ballast, then you have extra cost in the circuit hardware, and then you need labor cost for the circuit, and then there's the efficiency of the circuit too. So not all of these, you can't just compare bulbs directly to bulbs because some of them require extra circuitry. So the cost of light in energy, I'm going to use this mouse over here. So we have 1 over lumens times the lamp cost, the lamp labor cost over the lamp lifetime, circuit cost, circuit labor over circuit lifetime, all of that plus lamp power over circuit efficiency times energy cost in dollars per watt hour. And when you look at that, the total cost of light, about 82%, this says, is the energy that it takes to make it and use it and run it. This 13% is labor, then there's some parts you got to buy, and then you got to get rid of the old bulbs. There's non-negligible cost to society. Shift in commercial focus to electronics and high-efficiency lighting. So Osram is a company that sells lighting, and they were saying in 1999, the incandescent was 13%, the electronics to run lights were 22%, and other was 65%, I don't know what other is. Now incandescent's 10%, electronics is half of the cost, because they're getting more into compact fluorescents and things with ballasts and circuitry and so forth. Oh boy, here is a chart of various costs. Let me run through this. So we have on the left here's a bunch of different kind of light bulbs. Lamp life, mean lumens, lamp power. These are all the things, lamp cost, labor cost, circuit labor cost, that went into those calculations before. And then, so some light bulbs are cheaper than others, but some last longer than others. So how do you make a judgment about which one to buy? And this data, I believe, is from 2010. It's fairly recent. This is, there was a Department of Energy research group, and they generated this. Anyways, this is cost per 1,000 lumens measured at 1,000 hours, because they have different lifetimes. So standard incandescent's about $10. Halogen incandescent, more expensive. Taking into account all these different costs and the CRI. So they took a factor of how nice of lighting is it. A white LED, whoa, very expensive 3 or 4 years ago, coming down. CFL, compact fluorescent, is $7.50. Linear fluorescent lights, like these, $10. So it's about a wash in terms of cost when you take into account labors and circuits and lifetimes and so forth with incandescents. Metal halide is very cheap, and high pressure sodium is extremely cheap. They don't have a good CRI. Where's the CRI? 21. Not very good. You don't go pick out your makeup under the street light. But if you're going to put 1,000 street lights in, all you got to do is light up the street so people don't crash. I'm thinking that's a good investment. Most companies expect a return on investment within 2 to 5 years. Usually consumers, they mostly probably only just say, well, which one's more expensive, and they buy that without thinking about the lifetime. So they might consider purchase price or maybe the cost in the first 1,000 hours or so. So incandescent lights, they work by running a current through a filament. The current heats up the filament, the thing gets hot enough, it glows, it gives off light. It's usually a tungsten wire. The bulb is mostly vacuum inside there. That's why it makes a funny sound when you break them. But there's a small amount of an inert gas in there. That's to prevent oxidation of the filament and to help keep particles from the filament from evaporating off. As they get sputtered off, or however they get off there from the heat, eventually the filament will wear through and break. The nice thing about incandescents is they operate directly off the power in the wall. So we don't need any circuitry like we do with LEDs, for example. You can run them AC or DC, that's nice, so you can use them with batteries. The life decreases rapidly with temperature, so that's important. And also when they're on, the filament is hot, it gets soft, so they're susceptible to vibration. So we used to use these in car headlights, and not so much anymore. Now they use halogen kinds of incandescents, which work better. So these improve life at high temperatures. Halogen is an incandescent with, again, a halogen gas. The performance of incandescents is great CRI-wise, and this is the color temperature, about 3000 K. I don't have a plot of color temperature. Here's a cool close-up of a really cool-looking filament. I just had to put that in because I could. Lifetime might be 1,000 hours. Efficacy, 40-watt tungsten might give you 12.6 lumens per watt, so small efficacy. 100-watt tungsten, 2.6, quartz halogen, 3.5, a little bit better. Theoretical limit at this color temperature is 95 lumens per watt. So you're not getting a lot of lumens per watt. Where do you think most of the energy in an incandescent bulb is going?
Heat.
Heat. That's right. The cost is about 20 cents per kilolumen to up about 50 cents per kilolumen. And this is a picture of the, and you never thought of that light bulbs were that complicated, did you? Look at all these parts they had to label. I got this off of bulbs.com, now you know. All kinds of interesting parts in there. Discharge lamps, like neon or fluorescent, the way these guys work is they're an electrical discharge through an ionized gas. So there's a gas in that tube, and there's electrodes at either end. And ionized means we put a gigundo voltage between the two ends, and a high electric field gives the gases energies, and they move around fast because they have a lot of energy. They crash into each other, knock off electrons, and that's called ionizing. So it's a plasma in there, sort of like flame, but not quite. And glass quartz ceramic tube, high voltage. They put a noble gas in there, like neon is a classic example, with mercury, sodium, and metal halides. The electrons again collide with the gas, so the electrons get spewed off. Well, actually, the electrons get spewed off from the electrodes. There's a high electric field. The electrons go screaming down the tube because the electric field crash into the gas molecules and when the electrons collide, the metal atoms emit a photon, which might be light, or it might be in the ultraviolet range where we can't see it, but it's a high energy photon, and when it strikes the phosphor on the tube, so the inside of the tube is lined with a white phosphor, that's why you can't see through the tubes. So when those UV photons hit that phosphor, it makes it glow, and that's how you get white light. UV lamps use phosphor to down convert to visible technology. So fluorescent lighting, this is linear fluorescent, compact fluorescent, cold cathode. These are the ones that we used to have in our laptops and still do to some extent, but they're going more and more to LEDs because LEDs are coming down in cost. So it's a very long, thin tube, cold cathode, who cares? But anyway, so they would light up very evenly and illuminate the back of your liquid crystal monitor. This is EFL, Eternal FL. I didn't look in to see what that was about. I found a picture of one, but I don't know how it works and what separates that. So you'll see these again. Some people put them in their homes. In my home, they're in the basement where I don't care what the colors are. But in my living space, I prefer something a little bit nicer. Offices, of course, because they're fairly cheap. LCD backlighting like shown there. Then you have high intensity discharge lights. These are very efficient for area lighting, and they're used in cars. So here is, this says factory xenon. I don't know what these colored arrows is. This red arrow, I can't read that. Maybe I can read it over on this, maybe the CIE chromaticity jar. This says our xenon 8000K. So whatever company I stole this picture from, this is their light bulb. This is factory xenon 4300. So these are the color temperatures. Factory halogen 3200K. Come to that later. There's so much fun, it's just hard to decide what order to have all the fun in. Okay, so high intensity discharge used for area lighting and automotive headlights, for example. Then there's specialty like neon lights, tanning lamps, flashes, and strobes. The performance of discharge lamps are in the 5 to 85 range. There's a huge range of how good the color is. These are spooky. I don't like those blue lights. Cold cathode, 3000K to 7000. Oh, sorry, this is color temperature. Lifetime, 10,000 to 20,000 hours, so they last longer than incandescents. Efficacy, 30 to 150 lumens per watt. More efficient in terms of producing light than incandescent. Incandescent was, what was it? What was the lumens per watt? Does anyone remember? Lumens per watt, 12, 17 in that range. These are 5 to 85, so they can be lousy, I guess, but they can be good. Oh, sorry, I was looking at the wrong thing. 30 to 150, so these are better. There's another point I was going to make, but I forgot what it is. Discharge lamps. This is more pictures of discharge lamps. Again, the same numbers we had before. Cost is about 40 cents per kilolumen up to $3 per kilolumen. Oh, I know, I was going to say, so the efficacy is how many lumens you get out for how many watts you put in. Incandescents were low, and we said the most of the light went to heat. So in a fluorescent bulb, if you grab it while it's on, you don't get a burn, right? So they're not as hot. Here's some pictures of crazy compact fluorescents. I don't think they're quite standardized yet. This is cold cathode fluorescence like you might use to backlight a liquid crystal. Compact fluorescence, high intensity discharge, efficient, or eternal fluorescence, sorry, and then standard old basement workshop tubes. Inside a fluorescent lamp, here's one end, there's this electrode, so there's still a filament in there, and when there's a giant voltage between this end and the other end over here, and that scares the electrons off and they get accelerated. Here's the internal phosphorus coating. Here's a little pool of mercury that you hope will vaporize, and that helps the life of the thing. There's an inert gas in here. Is it neon? Probably. I'm not sure what other gases they might use. Does it say in here? No. Okay. Solid state lighting. This is LEDs. When I was young, no fooling, in college, we had these calculators and they had LED displays, and the displays were so inefficient that they put a little plastic lens over each one. Have you ever seen those in a museum? And the numbers would look all distorted because the displays themselves were tiny. They tried to magnify them so you could see them, which of course reduced and made the image bigger, so there was less light per area on the image, so they looked dimmer but bigger, and they sucked up energy and they were red. We had red, red, red. And then one day, we had high efficiency red. So the red ones were about 660 nanometers. High efficiency red were 635, the kind of orangey red. And we were very happy, and all was well with the world, and stayed like that for a while. Then we got yellow. Well, we got orange, and then we got yellow, and we were very excited. And it stayed that way for 10 years. We had yellow, and that's the best we could do. Then one day, we got green LEDs. I couldn't believe it. It was like, we're saved, we have green, yay, green. Very weak, very inefficient. They're much better now. They have much better materials now. If you want to know why, major in electrical engineering, we have courses you can take. So we had green, and then it stayed there forever. And you couldn't make an LED TV or a screen or anything, because in order to display all the pictures, remember, you need red, green, and blue. We didn't have blue. So LEDs were not used for lighting. They were used for, when I say lamp, I mean like on-off kind of lamp, like the power lamp, you know, things tell you on or off, Christmas lights. We didn't even use them for Christmas lights back then, because we didn't have blue. We only had these colors. Then one day we got blue. We have some materials advances, and now they make ultraviolet LEDs, and you're probably saying, well, what's the point of that? And the answer is, if you want a white LED, see, LEDs emit just one color. White is all the colors. So what they do to make a white LED, one approach is to put a blue, red, and green chip in the same thing, light them all up, and it looks kind of white. But now that they can make ultraviolet LEDs, they actually put a phosphor inside there, and the ultraviolet light excites the phosphor, and it looks white. I'm not saying they're efficient, but actually they're better than a lot of things. But you know, from my point of view, blue LEDs are a miracle. I can't believe in white LEDs. It's like that is coming. You know, when I was young, there was no such thing as a white LED. We couldn't even imagine it existed because LEDs only emit in one color. So who would have thought you'd put a phosphor on there? So the first LEDs were actually infrared. So we had them for fiber optics. And we spent a lot of energy. The first ones emitted in the near infrared in the 700 range, and then we spent a lot of time working to push them out into the further infrared to 1.3 microns, 1300 nanometers. Why? Because that's where the optical fibers had a window of low loss. And there's another one, even lower loss, at 1.55. So when I was young, we had infrared lasers and LEDs, and then we had long wavelength, and long wavelength meant 1.3. When we got to 1.55, we'd run out of adjectives. We had to just say 1.55. So we spent a lot of effort working in that direction. Now they're working the other direction. Okay. What
makes it harder to get the green compared to like the red? Like an LED isn't just about getting the right band gap.
Yes. Right. So the question is, why is it harder to make a green LED? There are some properties. So there are semiconductors. There's semiconductor junctions. Some people are electrical engineers and know that, but if you don't, now you do. Oh, now we'll have to charge you extra tuition for that. And the materials have to be direct gap. So there's a quantum mechanical property of these materials, and the ones that had the right band gaps were indirect gap. They weren't efficient. In fact, silicon, which we use for photodiodes, is a very lousy detector because it's indirect gap. Indirect gap basically means it's not good for photonics. It's not good for emission. It's not good for detection. We use silicon anyways because it's cheap. It's unbelievably cheap, and we have invested 50, 70 years of technology in making devices out of silicon, so we're good at that. But it's not very good for optical things. So the problem was materials. We just didn't have the right materials. Then we invented band gap engineering, and you can adjust the quantum wells. So by adjusting the thickness of the quantum wells, you can adjust the wavelength of the light emitted. So, and you know that, did I tell you about the clean room in the basement of Dries? Did I tell you to go down there and look in the window? Oh, well, you missed that class. Oh. So in the basement of Dries, there's a clean room. Go down to the basement, take this elevator right here outside after class, go down the basement, walk around till you see the window and look in there, and in there they can grow materials, exotic materials, one atom thick at a time, so they can make indium gallium arsenide phosphide with lemon freshened borax and stuff, and make materials that have these properties that we didn't have when I was young. Now, but we have to make the materials. We have to grow them out of atoms. We can't go and mine them. That's why.
Oh,
yeah. Yeah, so if you want to know more about that, change your major to electrical engineering and take ECE 3030. I'll write you a letter of recommendation. All right, so To get white LEDs, we just said this, white's a color, combination of colors, you can't make it with an LED. So one way was to use the 3 LEDs, that way, so if you had 3 LEDs, here's a blue one, a green one, and a red one, when you looked at that with the eye, it would look white, because they're tiny and they're all really close together, so you just see it as a white dot. But my impression is that they're mostly doing it with phosphors now. With the red, green, blue, again, you're limited to what's your red, what's your green, what's your blue on the chromaticity diagram. Who knows what these are pictures of? I won't belabor that. Oh, I see. This is nanocluster. So this is a part of powder of some kind of nano, probably quantum well stuff. Did anything happen? Oh, it looks like a picture grew.
Just a triangle.
Yeah, this triangle just grew here. But I forgot what point I was trying to make at the time. The RGB can't render some colors very well. That's important to remember. And they degrade at different rates. So the red ones are the most well established. They have longer lifetimes. And so as the red one stays good and the green one kind of gets poor over time, the colors will change. That's another reason to go to phosphors. So here's the phosphor one. So the idea is you have this blue or ultraviolet luminescence from the LED, and then those photons excite the phosphor, and you get this phosphorescence, which is wider band, and that makes it look white. But, of course, you have 2 energy changes. One is you got to convert electricity to the blue, and then you got to convert the blue to the white, so there's losses at those stages. Ow. More about solid state lighting. So here's some pictures of some LEDs. This one here, I can't reach it on the screen. This one is a cute little surface mount LED. It's very tiny. You put it on a board so it'll be behind the window that looks out, and that's the power, tells you the power's on. Here's a chip of some kind with some emission areas. This looks like it's got several chips on there to make it look brighter. Performance of these guys, 50,000 hours, they last a long time. Semiconductors are very reliable, well-established technology, and in order to even test the lifetime, we have to come up with accelerated life tests. So we heat them up and do things to them to make them age faster, and then try to calculate, well, if this had been at a normal temperature, how long would it have lasted? And that's how we come up with these numbers, because who's got 50,000 hours to wait to get the answer? Efficacy, 20 to 60 lumens per watt for commercially available stuff in research labs. This is 3-year-old data, by the way. 120 to 200 lumens per watt. Some Turkish university claimed 300 lumens per watt. I didn't see that paper, so this is stuff I got from the guy from Colorado. Cost $50 to $150 per kilolumen. But it's coming down. This is 3-year-old data, and it's coming down. If you've been to the grocery store, you see more and more LED lights in the light bulb aisle, because now they're not so outrageously expensive that somebody might actually buy them. Here is Department of Energy solid state lighting multi-year plan R&D update, and these some of these are projections. This data is from 2008, so these 3 columns are projections. Efficacy in the lab in lumens per watt, 120 was a record, and they expected it to get up to about 200. And we saw that some Turkish place said they had 300. Efficacy for commercial cool white, lumens per watt, 84 up to 188. Commercial warm white, you can see the numbers. OEM device price product. This is dollars per kilolumen. So they're hoping that this is LEDs. I think they're comparing it to other things. It doesn't say that, but I believe that's what this is. And I think they're saying that this is what the price of LEDs will be. So they're expecting the price to come down really fast, and it has been. More on lighting. Incandescent bulb, 10% efficient, means 10% of the energy is converted to light. So the other 90% is converted to heat. Did anyone have a Suzy bake oven? Probably you guys were all guys that didn't have that. When I was little, they had these little ovens, they put a light bulb in there, and little girls could put things in there and toast them and cook little cakes and stuff. And that's all it was, incandescent bulb. Now, if you have an incandescent bulb in your house, you turn it on, and you're getting that heat, right? You're using it to heat your house, so it counts, right? Except for in summer when it kind of counts against you. So in summer, you're paying to keep your house cool. But you're using electrical energy to produce heat energy. Remember, we said we didn't like to do that because here's the coal, so we mine the coal. This here, it's coming off a barge, it's transported, there's energy here. We burn stuff, there's energy lost here. In fact, I think I have some cute little arrows that will appear. So there's a loss of heat coming out of the cooling tower there. There's losses in conversion in the boiler. There's losses in the steam turning the turbine. Turbine has friction. There's loss in the transformer that takes it up to the transmission line. The transmission line has loss, and then you turn it back into heat at your heater. So we don't really like to generate heat from electricity. It's better to generate it by burning the gas directly. So I guess that answers the question about the dryer from earlier. So if we think about how many kilowatt hours per day per person does someone in Cambridge use, McKay estimates about 4 kilowatt hours per day. It's not a significant consumer of energy. Even though it looks like we're spending a lot of energy, it's small. And remember how you had to do 100 push-ups in, what was it, 100 push-ups in a minute with 128 other people to keep 100-watt light bulb. It was you who could do that, right? Weren't you the guy who said you could?
I think that was
that you?
Spencer.
That was Spencer again? Alright, well, it took 125 people doing push-ups, 100 push-ups a minute to burn a 100-watt light bulb. And look at what a tiny fraction of our consumption that really is. If you run 10 incandescent lights for 5 hours per day, it might be 5 kilowatt hours per day. If you use 10 low energy lights for 5 hours per day, you can knock that down to a tenth of that. If you have 2 people in the house, that's what he used to make this assumption, plus what's used to work. Figured out that he could neglect public lighting and car lighting because it just wasn't significant. So, let's talk about, oh, wait a minute. I want to go back because I have some fun here. I want to talk about a liquid crystal monitor. Do I have a picture of one? Maybe I don't. Well, here's a monitor. We use some kind of RGB on liquid crystals. Liquid crystals do not emit light. Right? Liquid crystals manipulate light by messing with the polarization. And I happen to have some polarizers here for your viewing pleasure. So what liquid crystals do, I recommend you each take 3 of these. I'll take 3. You don't get to keep them. LEDs emit light. Fluorescent tubes emit light. Sodium lamps emit light. Liquid crystals do not emit light. They have to be backlit. So there's a light source behind them, which was that right there, this complex fluorescent, and then the liquid crystals in front of it manipulate the light. They can turn it on or off. So what happens is there's a polarizer. Polarizer polarizes the light, just like your driving glasses polarize your light. Then there's another polarizer on the front, and there's liquid crystal molecules in between. The liquid crystal molecules have a property that they can screw up the polarization. So if you take your 2 polarizers and turn one of them, you should be able to extinguish the light. I don't know, can the distance guys see this? Maybe I'll try it on the document camera as soon as I figure out how. Right projector, document camera. Hello, document camera, how do I turn you on? That looks like an important button. I don't know what that does. Power on? Does anyone know how to work this? Menu. Well, maybe this isn't a good use of time. There we go. Let me put something. Problem is, they won't be able to see this because we can't look at it from the back. Darn. Sorry, distance guys. Plus, the, okay. Go back to the podium computer. Sorry about that. Anyways, if you have a liquid crystal display on your computer, if you take your driving glasses and you rotate them, you should be able to see the color go out, or sometimes it'll just change a lot. But that's what liquid crystals do. So when you apply voltage, they do screw up the polarization and the light doesn't get out. When you don't apply voltage, it doesn't screw up the polarization, the light gets out. Or you can make it the other way around. Oh, this has a green shadow. I can use a document camera for this. Document camera. I have here a calculator that the distance guys also can't see because the light is too poor. You guys can see it. Let me try. Right screen close up. I don't think it's going to show up. But if I have a polarizer, so the liquid crystal in this calculator, there's a polarizer on the front. The light comes down into the liquid crystal, gets polarized by the polarizer on the front, and then where the liquid crystal molecules don't rotate the polarization, the light reflects off the mirror on the back of the display and comes back out, and that's why it looks silvery. I can apply voltage to the segments here, different segments. I can press different numbers here, and that screws up the polarization so that it rotates and the light can't come out. So it goes in, let's say, vertically polarized, and where these segments are, it'll come out horizontally polarized, it gets blocked. So if I take this polarizer and I hold it in front of here, dang, you can't see that. Too bad. Well, I tried. So you may wonder, why did I give you 3 polarizers? Let me go back to this and this. Because if you have one polarizer and you hold it up to light and you take the other one and you cross them, you believe that, then so you have the light gets polarized by the first one, the second one blocks the polarization so no light gets through. What happens if you take another one at 45 degrees and stick it between them? Put one between them and rotate that. What do you see? Distance guys, I'm afraid you can't see it. Distance guys, you have to come to my office during office hours, or I'll have some polarizers and you can try them. If the first 2 are crossed so no light gets through, and then you put the other one between them at 45 degrees, you will see some light gets through in that section. Do you see that? So it was being blocked, and by putting something between them, you kind of unblock it. So for those of you who are engineers, if you believe in vectors, the first polarizer polarizes the light vertically, so that vector has a vertical component only. The second polarizer that you add is crossed, so its vector is horizontal. The vertical light has no component in the horizontal direction and no light gets through. When you put this one in between them at 45, the vertically polarized light does have a component on the 45 axis. So some part of that light gets through, but that light is now polarized at 45 degrees, which has a component in horizontal direction. So vectors are true. How cool is that? All right, well, I digress. So I conveniently see that we're out of time. So I think I will talk about offshore wind. Actually, you know what? We still have 7 minutes. Let's keep going because I can cover offshore wind. We don't have a lot to say about that. Because we're Ohio, we don't have any coasts. But Denmark, Belgium, Sweden, Finland, Germany, UK, these guys, they all have some preliminary offshore wind. There isn't a lot of it, but it's starting to get implemented. There's 1471 megawatts of offshore wind turbines in Europe. At least this was true in 2011 when I made this slide. I haven't updated it. And they generated electricity most of the time. Out in the ocean, the wind is blowing most of the time. So it's a good place from that point of view to put wind. And here is an example of a grid. So these things between them, I think, are to help keep them rigid. And here's a close-up of the turbine. This is a Vespa turbine, which is the kind we have in Northwest Ohio. We have no offshore wind farms in the U.S. People have been talking about it. Do we have a wind map of the U.S.? No. Turns out we have a lot of wind off the Pacific coast, not so much the Atlantic coast. Denmark gets a lot of energy from wind. How much do they get? I don't know how much they get from offshore, but they get 20%, 19 of their total energy from wind, including onshore and offshore. And the reason was they subsidize it. So they let the individual people buy wind energy. It's a cool picture. I think I have oh no, that's coming up later. So here's a list of a bunch of wind farms. These are wind farms with nice Scandinavian looking names. This is Fredrikshavn and Salmsted, I don't know, goofy Scandinavian thing. Capacity megawatt hours, so that one at the top is 209. That's 91 turbines. They're Siemens, this brand. Where are they? There's a location, 2009. How much did it cost to build? 470 million euros. Capacity, that's a cap.fac, and I think it's the capacity, percent capacity, nameplate capacity, but I'm not sure. Depth range, so the depths are less than 20 meters. Some of them are just a few meters deep. How far from shore? These are the kilometers distance from shore, where it's still shallow enough to implement them efficiently. Look, these are all Danish, and who owns them and so forth. Okay, so Denmark, they started building windmills actually in the 1970s. So the government offered tax exemption to citizens if they would generate their own electricity. So some people bought turbines and put them on their houses, and other people bought shares in wind farm cooperatives. So even if the wind farm cooperative is offshore, like us buying energy, quote, buying energy from Blue Creek up in northwest Ohio, we're really buying energy we're getting our energy from the grid, but we're giving them money to put the energy into the grid on our behalf from a wind source. So over 150,000 Danes were involved by 2004. Other countries have tried this kind of incentive, but they weren't as successful as Denmark, so I guess Danes rule. And they plan to increase wind to 50% of their total power needs. So Denmark's not a huge country, but I'm guessing they have some wind. I know they have some coast. So offshore wind, the advantages are the winds are stronger and steadier in the ocean. Steady is also important. If you can find shallow water with a lot of wind, that's good. So shallow water depth, you want 25 to 30 meters, which is interesting, because guess what? That's about the average depth of Lake Erie. And we saw earlier that Lake Erie has a boatload of wind potential. There's some nice strong winds out there. Deep offshore wind is not cost effective at present. So you need a coast with wind that's not too deep. But there are other pros and cons. So one big pro is you're not using up valuable land space. So you can grow more food or biofuels or put solar panels there. The winds are higher in the ocean and they're more constant. On the other hand, it's expensive to put them in the water. It's difficult to build. And it require high maintenance. So every one of those turbines in a Danish installation had to be replaced because it's a caustic saline environment and it erodes everything. And Ohio's not near the ocean, but we do have Lake Erie, which incidentally is fresh water. So Lake Erie is shallow, that's good. We have strong winds, that's good. We have steady winds, that's good. We have to transmit power to the rest of the state. That incurs losses, but it beats transmitting power from Lake Erie than from, say, Kansas. Lake Erie's closer. We'd have to build wind turbines out on the water, that's expensive, but if we would do that, and people are talking about it, hasn't happened yet, that would be beneficial. They have to maintain them on the water, that's expensive, but at least we don't have salt water. So we have that advantage. And we'll explore this topic further later on. Stay tuned. And then I love this thing from the book. He says windmills kill birds, right? She goes, well, how many windmills kill birds? And he came up with 30,000 in Denmark, caused by wind turbines and cars, and animal deaths in Britain caused by cats. So this is cars in Denmark, cats in England. So that's a pretty impressive graphic. What's the flaw in the reasoning here?
It's not per turbine, maybe.
Yeah, there's a lot fewer turbines than there are cats. So of course cats are going to have more. But I've still seen other data that says that you still have, you also have a lot of birds killed by flying into windows. Guess what? That's us. But we have a lot more windows than turbines. I don't know if this is a problem or not. People saying it disturbs bats too. And I don't know how big a problem it is. It would be less of a problem out on the ocean or Lake Erie because there's only seagulls there. Nobody likes them anyways. Sky rats. All right, so let's stop here because class is over. We'll start up with gadgets the next time. And if you want to play with these polarizers, that's fine. You get a free book. So come up here and get that. And I will see the rest of you guys on Monday.